countdown and liftoff went smoothly for America's first space station. From Kennedy Space Center, a Saturn V rocket lifted Skylab through a bank of clouds and into perfect orbit high above the Earth on the afternoon of May 14, 1973. But signals from the spacecraft almost immediately began to unfold a grim story to flight controllers and engineering support teams on the ground. The extent of the emergency was pieced together by support team personnel, including George Hardy, manager of Skylab Program Engineering and Integration.
Very soon after launch, it was obvious that we had lost part or all of the shield around the orbital workshop. This exposed the gold foil surface directly to the sun rays. Whereas we had deployed the ATM solar rays, there was no evidence that we had properly deployed the orbital workshop solar rays, and in fact, we later learned that one of those solar rays had been lost during the boost phase. The other array was partially deployed, but not completely deployed. With the gold foil exposed directly to the sun's rays, the temperature inside the orbital workshop, in the areas you can see here, was increasing rapidly. Soon after we'd achieved orbit, it was obvious that the temperatures inside the orbital workshop were going well above design limits. In fact, the air temperature was approaching 130 degrees Fahrenheit. We were concerned about the condition of film, food, and other equipment. We were also concerned about the plastic material, insulation material that's behind the inner liner of the orbital workshop. At high temperatures, there was danger of this material giving off possible toxic gases and making the workshop uninhabitable.
There was no immediate danger to the other Skylab modules, the airlock module, the docking module, and the Apollo telescope mount. And the telescope mount's windmill-shaped solar array was still intact and producing electrical power. But 55% of Skylab's electrical system was sapped by the damage. Power was too meager for crewmen to live comfortably for weeks on end and carry on all of the ambitious scientific program. Skylab was on the verge of becoming a burnt-out derelict in space, unable to perform its planned 8-month investigation of space, the sun, and our own world. The full extent of Skylab's problems became known to support teams by late afternoon on May 14th, and it was clear that the first cruise, scheduled May 15th launch, must be canceled until major repair actions could be attempted. Response on the ground was prompt. Teams that had put 6 years of planning and work into Skylab began work hurriedly to save it, centering their efforts at Marshall Space Flight Center and Johnson Space Center. Marshall had provided the workshop and the docking and airlock modules, the telescope mount and launch vehicles. Johnson provided the Apollo command module. Other Space Center and industry personnel joined those already at Huntsville: design, manufacturing, and simulation specialists, procedures and stowage personnel from the Johnson Center at Houston, sail-making seamstresses from New Jersey and their stitching machines, and the astronauts, who were now landlocked until the troubles could be solved. A command module simulator was flown in from Houston. Flight control and mission support personnel tracked the Skylab troubles through the night. A troubleshooting team was formed in the Huntsville Operations Support Center from existing support teams. The team's starting point and level of attack were directed by Marshall Center Director Rocco Petrone in a telephone call to George Hobson, Environmental and Flight Support Chief.
Dr. Petrone told us that our first job was to get the temperatures under control. We had to move fast to keep the workshop from becoming uninhabitable. The next job was to find repair methods so that we could save the full mission. We were told to ask for anything we needed to accomplish this job.
Mission support engineers working with Houston Flight Control began the fight to contain workshop temperatures. They nosed the docking module up toward the sun, easing the blistering workshop into shadows. This held for one orbit. The sharp climb in temperatures was reversed, but the power from the telescope mount solar array to the batteries was cut off when it no longer faced the sun. Controllers angled the spacecraft back down 45 degrees for one orbit. The telescope mount solar array still would not supply power. The controllers maneuvered Skylab back to its normal flight angle. The solar array came to life, but temperatures again rose toward the safety limits for film and food. Personnel staffed support centers full around the clock, tending Skylab's troubled equipment, calculating maneuvers for rolling and jockeying it about. A quarter-degree drop in temperatures brought cheers. A quarter-degree rise brought dismay. Lightning disrupted power to Marshall's computers. The computation load was shunted to outside facilities for several hours. Some personnel did not leave their posts from dawn Monday through Wednesday night. Meals were slim, hours were long, and humors were short. Engineers and flight controllers won the first battle after 2 days, finding a flight angle for Skylab that would save the limited electrical power and most of the food and film. Earlier maneuvers had taken the workshop interior temperatures down to the range of 110 to 120 degrees. At the new flight angle, they were rising barely 1 or 2 degrees a day. Only occasional rolling of the spacecraft was necessary from time to time to warm Skylab's shaded side. 2 major problems remained, but hopes rose sharply for the personnel participating in the repair effort. Among them were Marshall Skylab Program Manager Leland Ballou and James Kingsbury, who was heading up the Marshall troubleshooting teams.
The problem encountered in Skylab 1, the loss of the micrometeoroid shield that gave us some very major systems temperature problems, had to be addressed in a very specific, different manner than the normal operation of a program. The center established a team headed by Jim Kingsbury that hit the problem head-on, direct, using members out of all of the industry, out of the other centers, that came up with changes that were flown up on Skylab 2, that when affected did solve our immediate thermal problem, as well as to get us into a situation where we did conduct a nominal Skylab 2 mission.
The first order of business was to provide some type of shield that could keep the sun off the hot side of the workshop here. There were several concepts being reviewed, many by both industry and government. We selected early in the game 3 or 4 and put primary emphasis on at least 2 of those, one of which was in an operation which could be done from within the spacecraft by extending a large umbrella out and unfolding it through a scientific airlock. That was pursued by JSC at Houston. We here at Marshall were pursuing a concept of going outside the spacecraft on an EVA and unfolding a large window-shaped type of shade over the hot area. And by the day after launch, we had progressed a good distance on both of these design concepts.
Many concepts were proposed and evaluated in conferences, the support team personnel wearing masks when they met with Skylab crewmen to abide by quarantine restrictions. Some concepts were inflatable devices. Others were sails or shades. One of them, a shade that could be deployed by an astronaut while standing in the command module alongside the Skylab. Various methods for deploying the shades were explored. Shades were made of materials on hand, but these became too heavy when treated with paint. The shade had to survive the bare ultraviolet rays of the sun, but could be no thicker than 1 or 2 thousandths of an inch. 3 more shades were made of a material flown to Huntsville from Houston, and they remained light enough after painting. A prototype 55-foot boom to deploy the shade was developed from equipment just like that on Skylab. The single boom grew into a twin pole arrangement by the night of May 16th. hardware fit was tested at the full-scale Skylab mock-up. Round-the-clock design and manufacturing teams produced a working twin-boom design that weighed 160 pounds, much too heavy. Rework got the weight down to 112 pounds. Structural tests were made. Other personnel searched for tools to free the jammed workshop solar wing that had to operate if Skylab was to have adequate power for experiments and crew comfort. Tools that would work on a long pole were needed to cut through the metal debris that kept the solar wing from deploying. Tree trimming devices were obtained at a hardware store. All available samples of power lineman cable cutters were flown in from a Missouri manufacturer. From these, solar wing salvage tools were developed. Tests were made to determine that the workshop's aluminum skin and insulation had not been seriously damaged by heat up to 325 degrees. Studies were made of the amount of lethal carbon monoxide and cyanate gas that could be present in the space station. Tube samplers were developed for the astronauts to test Skylab for presence of the gases. Support teams were now trying to prepare all of the Skylab repair equipment so that the crew, barred from launch on May 15th and again on May 20th, could fly to the space station on May 25th. The command module mock-up was positioned underwater in the zero-gravity simulator. A solar wing mock-up was installed, enmeshed in wire and other metal debris. Use of the cutting tools to clear away debris from the solar wing mock-up was tested by Skylab crewman Paul Weitz. Procedures for deploying the twin-boom 22 by 24-foot sunshade were checked by astronauts Schweikert, Musgrave, and Gibson on May 18th. Astronauts Gibson and Dean ran through a complete simulation on May 21st. On May 22nd, the shade was deployed vertically at the full-scale Skylab mock-up. Then the operation was repeated in the zero-gravity simulator. The space station repair equipment was ready by May 23rd. Sunshades, booms, and cutting tools were packaged. The parasol developed at Houston was tested there and packed in an existing 52-inch experiment canister. The command module stowage team took stock of the module's more than 800 stowage items, finding a way to eliminate 70 of them so that 150 repair and resupply items could be added. Ground controllers completed repeated remote purges of the space station atmosphere to remove toxic fumes that might be present. As Skylab circled the Earth May 25th on its 156th orbit, the crew and command module were launched from the Kennedy Center by a Saturn 1B rocket. They arrived near the space station by late afternoon. Captain Conrad maneuvered the command module around Skylab to survey its damage. From the command module, Weitz, held at the knees by Kerwin, made an unsuccessful attempt to pry loose the solar wing. Wearing gas masks, crewmen entered Skylab the next day, finding temperatures to be near 100 degrees and the atmosphere safely clear of toxic gases. Crewmen labored into the evening to get the large parasol deployed through an airlock in the workshop wall. Word of success came to support teams below in a call from the astronauts. She's up and the temperatures seem to be coming down. Inside, readings fell to 98 degrees, then to 88, then to 82. By May 29th, mission operations were proceeding routinely, but still on limited power. Testing showed that most of the space station equipment was able to function. Medical experiments and telescope mount observations of the sun were begun. Earth resources observations began on May 30th. Now the third major operation to save Skylab's experiment program was almost ready. Astronauts on the ground first worked out procedures for using the cutting tools. Then crewmen Conrad and Kerwin took the tools outside Skylab in a spacewalk on June 7th. Improvising a handrail from sections of the boom for the new sunshade, they maneuvered into position. With the cable cutters, they cut away the metal debris that held the solar wing. Then, pulling on it with a rope, they unjammed a hydraulic damper on the wing, and the 30-foot, 1-ton solar wing quickly unfolded to its proper position. But the wing's 3 panels of solar cells stopped their deployment less than halfway out. Ground controllers maneuvered the space station so the sun could heat the panel's frozen hydraulic dampers. All 3 panels deployed completely. Within 5 hours, the workshop solar wing was providing its full power to the Skylab electrical power system. Dedication of personnel during a bleak 10 days of emergency operations had paid off in flight. Their efforts were lauded by Marshal Director Dr. Petrone.
Hundreds of people, both in industry and government, worked together as a close-knit, well-integrated team to come up with solutions to save our stranded ship, the Skylab, 270 miles above Earth. The tasks were arduous, very demanding, and many people worked days on end without rest. But the results were both heartwarming and very beneficial to our total efforts in space, showing what men on the ground working with men in space can do.
Almost all of the original objectives of the 28-day mission were achieved. All medical experiments were conducted. 80% of the planned solar studies were carried out, yielding 17,000 frames of film that are 100 times more revealing than the best previously available. 11 of the 14 Earth resources experiments planned for this first mission were carried out. Information about 31 states and 6 foreign countries was obtained for 75 of the program's scientific investigators. One of the primary questions Skylab sought to answer by the end of its 8-month investigation was how effectively can man perform work in space? A clear answer came earlier than planned in the first Skylab crew's repair efforts, which made continuation of the manned missions possible. The answer was reinforced when the second crew, on August 16th, deployed the twin boom sunshade over the parasol. Workshop temperatures were further reduced. Astronaut and equipment efficiency rose above the levels that were projected before launch. And there was renewed optimism that Skylab's 3 full missions would be completed as scheduled.